60-degree temperature, but I am maintaining 80-degree temperature. Something is happened, and not that something here, right? So whatever happening, right? The peak is like appeared here. If the unwanted peak is appeared along with your material, means your material is not. If it is nano range also, but whatever concern is that dilution is there with your nanomaterial, right? And this is supported by the JCPDS card numbers. Every nanomaterial having unique JCPDS card number, right? You can check with the JCPDS card number, and if it is a JCPDS card number matched with your material, you are perfectly prepared your nanomaterial. Otherwise, it is not your hand, right? And what we like get from this XRD means we can know the size of the material using Devasier's formula. This is the D is the average crystal size. This is the formula for this, and we'll get a Williamson-Hall equation, strain calculation, and this is the particle size analyzer. It is working under the principle of dynamic light scatter, right? What we get from here means you will get the histogram under the Brownian motion. If the motion of the particle is high, the particle size is small. If the particle motion is low, the particle size is more. Sir, it is understand, but it is not understand. Can you explain? Yes. Just you can see the pattern like this, right? If the particle size is more, this vibration is very low. If the particle size is less, it is more, right? Like that only, we'll get the pattern like that. Based on that, we'll get the value. The mean value of the histogram is taken as the average particle size of the material. And this is the scanning electron microscope. Yeah. What is the advantage of scanning electron microscope is optical microscope, the magnification is only 4x. But it is the scanning electron microscope, it is a 10x, right? The depth of field is a 15.5 millimeter to 0.919, and the resolution is a 0.2 mm. But it is in the nanometer range resolution, and the depth of field is a 4 mm to 0.4 mm. That is the beauty of this scanning electron microscope, right? Whenever we start the analysis, whenever we submitted the material, they will go for the sputtering technique and make the material for the interaction of electrons and all. Right? You can see TiO2 nanoparticles, it is in the 1 micrometer, and this is the SnO2 nanoparticles, it is 1 micrometer. This is copper oxide and titanium dioxide composite material, right? 500 degrees, 600, 700 and 800 degree calcination temperatures, right? The XRD, semi-majors are like this. It is all my work only, right? There is no copyright and all, right? So this is the EDS pattern, right? What will get EDS means in one particular area you can click, right? You will get the elemental information of the material. That means if you want to prepare zinc oxide nanoparticles, whether it is zinc oxide or not, right? You can check with the EDS analysis. That means you can see very clearly the zinc percentage and oxygen percentage, 57% and 42%. The atomic percentage is also 24% and 72%. That means the 100%, I am telling that the material is zinc oxide. There is no contaminations or nothing, right? Yeah, this is a UV visible spectroscopy. It is working under a Beer-Lambert's law. It is also absorbance pattern, and I will tell you the energy dispersions and all. Right? Here we will get the peak. Here also same. Every nanomaterial having one unique peak number for the UV visible. Right? That means if your material is, for example, ZNO, it is having some number of UV visible spectroscopy. If you got the range of number, your material is confirmed. Otherwise, no. Right? For the energy band gap calculations and all. Yeah, this is the FDP-1D-AN. We can get the fingerprints and all here. I'll show you. Yeah. This is the SnO2, TiO2 nanoparticles for 500 degree temperature. You can see FDR images like this. This is a 600 degree calcination, 700 and 800. What are these? Are all the things, right? I mentioned that fingerprint region is there, right? You can see these two bonds are OH stretching bonds, and this is the weak water bond, and this is the C double bond O, and this is the ionic liquid. I already mentioned ionic liquid is the organic solvent in my material, right? This is the CH bond at 1100, and you can see that in the fingerprint region, right? I got the TiO2 nanoparticles and the SnO2 nanoparticles. That means the composite of SnO2 and the TiO2 is conformed with the FTIR. Likewise, only you have to compare with another characterization technique, and you will tell that your material is conformed. And this is the TGDTM. It is for weight loss calculation, right? You can see that the blue line. This is a thermogrametry. You can see the weight loss of your material from 100% to 98 around. That means 97 something. That means 3.3% of weight loss is there in your material whenever you heat the material, right? This is the ZnO TiO2 composite. What we get in differential thermogrametry means if we get any phase transformations in the material, you can get the bumps like this, right? This is called this ZnO TiO2 material getting some phase transformation. That's why we got the peak disturbed here, right? This is the third part. I'll finish the third part. Sir, I have only 10 minutes or 15 minutes? 10 minutes. Okay, I'll finish within 10 minutes with the fourth presentation. Stay with me, bear with me for 10 minutes. Sorry, truly confidential. Please, anyone taking any photos or